Alright, in this video in section 13.2 we're going to talk about sphere equations. Okay, so in order to describe a sphere we first need to talk about distance in R3. Okay, so let's go ahead and suppose we have 2 points, say P and Q, and we want to compute their distance d between them. Okay, well, as a first step in doing that, let's go ahead and first notice that this green distance d is the diagonal here of this box whose two corners, opposite corners there are P and Q, and then these side lengths just run parallel to the coordinate axes. Okay, now the next observation is to see that, oh, this distance d is also the hypotenuse of this triangle here, formed by the diagonal of the base of the box, and I'll go ahead and call that A, and then this height here of the box, and I'll go ahead and call that side length B. Okay, so let's go ahead now and find an expression for A in terms of the coordinates of P and Q. Now I've just gone ahead and copied this triangle of the base over here to the right, and notice A is just this triangle's hypotenuse. Okay, so let's take, say, the height of this triangle first. Okay, notice here we are just moving in the x direction, and we're starting here at P. So what's going to happen is that when I go from this point at P to this corner over here, I'm just simply changing the x coordinate, right? There's no y or z movement. So in other words, I'm going to go from an x coordinate of x1 for P up to an x coordinate of x2 for Q. So this side length would just be the difference in those x coordinates. Okay, and then likewise we're going to have for the base of the triangle, which is right here, we're going to go ahead and just change the y coordinates, right? There's no x or z movement now. So here we'd be going from a y coordinate of y1, and that's for P, up to this corner, which will have a y coordinate of y2 for Q. So the base of this triangle then would be the difference in the y coordinates of the points. Okay, great. So now what we're saying, since A is the hypotenuse of this triangle, we're saying that A squared will be the sum of the squares of, in this case, the difference in our x values, just x2 minus x1, and then the difference in the y values, so y2 minus y1. Okay, great. How about the side length B? What is that? Well, notice here we're just changing the z coordinate, right? There's no x or y movement there. And so here, right, all we're going to get is that B is simply going to be the difference in the z coordinates. So z2 minus z1. All right, great. So now let's go ahead and go back to this larger right triangle where D is the hypotenuse, and we'll apply the Pythagorean theorem to it. Okay, so we can say that D squared is equal to A squared plus B squared. Okay, so now if I open this up a little bit, I can say that D squared is going to be, well, what's A squared? It's right here, right? It's just the sum of the squares of the differences in our x coordinates there and then our y coordinates here. Okay, so this portion right here is just coming from our A squared that we just computed, and then we're going to go ahead and get, right, the sum of this with B squared, and so that's just going to be z2 minus z1 quantity squared. Okay, so this portion is coming from the B squared. All right, cool. And then of course we can go ahead and just take square roots, and we're going to come up with this is just simply the distance formula in R3, right? And notice this looks just like the distance formula in R2, except now we have, right, this addition of the square of the difference in the z coordinates, right? All right, cool. So now with this in place, let's go ahead and compute, say, the equation of a sphere. So for that, I'm just going to first make some space. All right, so let's say we have a sphere, and its center I'll go ahead and label as, say, C, and then this point out on the sphere we'll call P. And so what really defines a sphere, right? Well, this is going to just be the collection of all points P that are a fixed distance away from this point C. Okay, and we'll call that fixed distance R for radius, of course. And so really the defining condition here is that the distance from any point P to the center, we'll call it C, this distance has to be this fixed value of R. Okay, so now let's go ahead and open up this left side, okay, using that formula we just computed, right? The distance from P to C, well, let's go ahead and use some labels here. So I'll go ahead and label the point P, its coordinates can be, say, x, y, and z. And then we'll label, say, the point C with coordinates A, B, and little c, okay? And so if I'm going to apply the distance formula to P and C here, what I'm going to get is the square root of what? Well, it's going to be the sum of the squares of the differences in each respective coordinate, right? So in other words, it'd be x minus a quantity squared plus y minus b quantity squared plus z minus c quantity squared, and there we have it. Okay, and then again, that distance here on the left has to just always come out to be whatever the radius of the sphere is. Okay, so finally I'll go ahead and just square both sides, and so we're going to just get the sum of these squares on the left, and then on the right, we're going to wind up with just the square of the radius, okay? And if you compare this to the equation of a circle in the xy plane, it looks really just exactly the same thing, except now again, like we saw with the distance formula, we just have this extra z term here, right, from that extra dimension. Okay, cool. So this is great. We now have the equation of a sphere of radius r and center at A, B, and C. So now let's go ahead and check out an example. So here's our example. It says find an equation of the sphere with antipodal points 2, 2, 2, and 6, 8, 14. So what do I mean by antipodal points? I mean that these are points that are directly opposite on the sphere, okay? So if I were to draw a little graph here, maybe that here's our sphere, and then I'll go ahead and call this first point, let's call this point, say, P, and then I'll call this second point Q, okay? So P and Q, they are directly opposite. So if I, in other words, drew a line from P through C and then I kept going, I'm going to exit out of the sphere at the point Q. Okay? So our job is to find the equation of this sphere. And of course, the two things we need to know are, well, one, what are the coordinates of the center? And then two, right, what is the radius of the sphere, okay? So we can do those really in either order. So I'll go ahead here and say, label this as the radius. And one way we could do that is just say, well, since P and Q are directly opposite, right, on the sphere, then the the distance from P to Q would be twice the radius. In other words, it'd be the diameter, right, of the sphere. So let's go ahead and start by saying, all right, for the radius, let's first find the distance from P to Q. Okay, and so to do that, I'm going to go ahead and take the square root of, well, the difference in the x's. This would be 6 minus 2 quantity squared plus, and then 8 minus 2 quantity squared, and then finally 14 minus 2. So just subtracting coordinate-wise and then adding the sum of the squares. Now this is going to be the root of 4 squared plus 6 squared plus 12 squared, which, as you can check, comes out to a nice clean 14, okay? So the distance from P to Q is 14, so then that's telling us that the radius of the sphere would just be half of that, so it'd be 7, okay? So that's one key piece of info. The other thing we're going to need is the coordinates of the center, okay? And so for the center, one way we could do that is to say, look, the center is the point that's directly in between P and Q along this line segment. Or in other words, it's the midpoint of the line segment PQ. Okay? So as far as finding the coordinates, okay, what we could do is just simply take the average of the coordinate of each respective coordinate for P and Q. Okay, so here's what we can do, right? For C, the coordinates would be, well, just take the average of the x coordinates for P and Q, so it'd be 2 plus 6 divided by 2. Then for the y, it'd be 2 plus 8 divided by 2. And then finally, for the z, 2 plus 14 and divide that by 2. Or put another way, right, the coordinates of C there would be 4, comma, 10, comma, oh, excuse me there, not 10. Got to divide by 2, right? So 5, and then finally 8. All right, so there is our center. So now let's put that all together down here, right? So for our sphere, we will have for its equation, it would be the quantity x minus the x coordinate of the center, and that's 4 squared, plus the square of the difference between y and the y coordinate of the center, so that'd be 5 squared, and then we got finally z minus the z coordinate of the center, that's an 8 quantity squared, and that's going to equal, well, the square of our radius, which would be 49, right? Radius of 7. Okay, great. Well, that's a good place to stop. I'll see you in the next video.